is Tim Dolch from Hillsdale College, and I'm part of both the noise budget and interstellar medium mitigation groups, also known as IMM. And I'm going to tell you a little bit about what these two groups do for NANOGrav and how it fits into all of the other working groups. So here's a basic sketch of what happens with pulsar timing. We have a distant pulsar, and we have pulses that propagate between the Earth and pulsar. So here's the distant pulsar, presumably with a binary companion. Here's the Earth going around the Sun, and we predict these times of arrival. And that's all well and good. But a lot of things also happen in the process of that propagation of the pulses toward the Earth. Of course, one thing we hope happens that we can detect is gravitational waves. That perturbs the times of arrival of pulses. But a lot of other things also perturb those times of arrival. We can think about things intrinsic to the pulsars themselves for each individual pulsar. So the rotation might not be perfect in terms of regularity. We might get glitches. There's a sudden change in period or period derivative. We might get a radio frequency dependence of that emission. We call that profile evolution. We might get jitter, which is just the fact that no pulsar is perfectly regular. And there's always a intrinsic spread of those times of arrival about an average down at the single pulse level. We might have a lot that goes on at the Earth. So these days especially, we worry about the ephemerides errors. In other words, the whole model of our solar system that we need to predict time of arrival. And in particular, in relevance to these two groups, we worry about the interstellar medium and what that does. So we can have various chromatic dependencies, in other words, radio frequency dependent effects, unlike gravitational waves, which should affect every radio frequency in the same way. So what do we mean by noise? Well, we want to detect gravitational waves, but we need to know what the noise of our detector is. Now, if you're a LIGO, it's kind of easy to do. You have your entire instrument in front of you, so you can just measure the noise. But in our case, our instrument spans the galaxy, so we can't exactly walk to the other end of it and see how the test mass is vibrating or whatever noise source you would imagine. We have to characterize these things in other ways. So that's why when we search for gravitational waves, as you've heard in the other presentations, we always search for a signal and the noise. We're fitting a potential signal and the noise to our data simultaneously. We don't know what the noise is. We get signal and noise together. Now, a lot of that process happens in the detection and timing groups. So both those groups are always busy finding the most updated noise models. But in the noise budget group, we're of course involved with those groups because there's no sharp lines between the different working groups in NANOGrav. But in the noise budget, we're especially interested in characterizing our gravitational wave detector noise independently from just timing models. So we're looking at having other physical models before you do a timing model that can characterize what sort of noise is in individual pulsars, or their lines of sight, or at the Earth, or in the pulsar timing array as a whole. So to take an example, this image here is a LIGO noise curve. So we have gravitational wave frequencies here, vibration frequencies of the detector, and here we have strain, so that tiny displacement due to a gravitational wave. And so actually it's not strain, it's delta L. Strain is delta L over L. And you can see that different frequencies were more sensitive. If you go too high, you're not so sensitive anymore. Same if you're too low. So you want this noise to be as low as possible, and then hopefully the signal will poke up above there, and that's what happened with the LIGO detections. Well, we can make a similar plot for a pulsar in principle. So here we have gravitational wave frequencies, and notice we're now about 10 orders of magnitude lower than the previous plot. It's because nanohertz gravitational waves are very long period waves, because supermassive black holes are much more massive than the black holes LIGO detected. Here we have something called power spectral density, and that's just in terms of our noise, what frequencies of noise are most dominant. And so what this plot here that Jim Cordes made is showing is that we can, just like LIGO does for a particular pulsar, we can decompose those noise levels as a function of frequency into different processes. So here we have different sorts of white noise. Jitter noise is fluctuation of pulse emission times I talked about a moment ago. We have things from the interstellar medium, diffractive interstellar scintillation, that's what that means. So that has a different noise spectrum on here. We can have spin noise, which is the long-term wandering of arrival times from regularity. And of course, we can have gravitational wave signals as well in here. So this is an example plot for a real pulsar, in this case J1713. Here's what it looks like. So all these different colors on here represent different noise processes that have been modeled that we can all add together to get a total noise value. If we translate this directly to gravitational wave strain, it looks like this. So we have various noise levels, and we have the maximum strain we could detect here as a function of those different noise levels. So these sort of high-level plots, this is again J1713, the best pulsar in our array. We can in principle make these plots for all the pulsars in our timing array, and that's kind of the long-term goal of the noise budget group. So noise descriptions, due to the need for them with pulsar timing arrays, have actually advanced quite a bit in the last 5 to 10 years. If you look at these papers, there's quite a few of them that are pretty recent. And this is a dissection of the different noise processes into different physical reasons. And I won't describe all of these right now, but I'll talk about a few of them in these slides. But the main distinctions between these processes are, on the one hand, those processes that are deterministic and those that are stochastic. In fact, the deterministic ones aren't really noise as such. I'm really talking about these things over here. But things that are deterministic we get from long-term timing, and those terms are those determine our times of arrival. So this means solar system barycenter here. And once we time a particular pulsar for a long time, we know these deterministic terms pretty well. But those are the things we can predict. So, the Earth's orbit about the sun, a pulsar and its binary in their orbits, those are deterministic things. Once we nail down a number of those orbits, we can basically predict those forever. There are also stochastic terms, which are all of those noise processes, you could say, or physical processes, that change times of arrival in ways we can't predict. So, for example, in the interstellar medium, what's changing our times of arrival are little clumps of ionized electrons between us and the pulsar. Well, we can't predict which clump will come in the line of sight until it comes. There's no independent way to get a handle on that, no good way. So all we can do is measure those times of arrival as they happen and statistically characterize them. But we call those stochastic terms because there's a random process behind it. That's what stochastic means. And we also have systematic errors. And those are things that are in principle deterministic. So observatory clocks, you hope that that's a regular thing. But in the long term, there might be a noise process underneath there that's also that's not deterministic, that we measure with time, but we have to take into account in our noise models. So having nailed these three things, we hope to get changes in time of arrival due to gravitational waves. So we can sort these out in a number of ways. If they're interstellar medium effects, we expect there to be frequency dependence. For other effects, there's not that sort of dependence. So in timing residuals, which you've probably seen a lot of by now in these talks, we have different statistical properties of what those residuals look like. If they're basically a straight line but with some uniform fuzziness like that, those are white noise residuals. And we can decompose that white noise into different sources. So we have radiometer noise, which is just the noise in the telescope itself and the receivers. You limit that by cooling the receivers, but it's never totally gone. Pulse jitter, as I mentioned briefly before, is the pulsar's own noise, as it were, the fact that it's not perfectly regular in its pulsations from pulse to pulse. And we can also have white noise just from the interstellar medium. So you can add those together to get our total white noise, what it should be. Here's an example of jitter noise. So we have, on the left here is an imaginary perfect pulsar. Oh, if that only existed. That has essentially a delta function, or absolute predicted time of arrival. In reality, every pulsar at some level has this slight wandering of single pulse arrival times. Now you average these together in pulse folding, and the noise gets a lot better. But if you go down to single pulses, there's this error bar that you can't avoid. Now, if you average all these single pulses together, they look something like this. So the width of this averaged pulse has a limit. So even if you timed a pulsar for the better part of a day, and you averaged all those together, you would still be limited by this intrinsic wandering or pulse jitter. Now, even that you can beat down, but it takes a long time. The only way to beat it down is to observe for longer per day, and we don't have that kind of time, even though we have 900 hours of telescope time a year. So this is a paper that Michael Lamb in the Noise Budget group recently published. Actually, it's almost a year ago now. But this is actually almost 2 years ago now. But these are measurements of pulse jitter for all of the pulsars in our timing array. And it's nice because it's a direct physical measurement of this noise process. So one way to do it is to fit for it in your timing model. When you take all the pulsars together and characterize how all of their times of arrival should change. But you can also do it just by measuring pulse signal to noise when you look at particular observations. So that's what's going on here. Now, transitioning a little bit to the interstellar medium mitigation group, we have a lot that happens, like I said, due to the interstellar medium. We have white noise terms, and that happens from the fact that the interstellar medium diffracts radio signals. So the interstellar medium is chunky. There are pockets of density. This is the ionized interstellar medium. So the pulsar source will get diffracted, and as a result, it makes back here toward the Earth an interference pattern. And that interference pattern is what we see across frequency here, and it changes with time over the scale of hours in this case. That's pulsar twinkling. It's the exact same process you see when a star twinkles visually. So that statistical uncertainty on the short term is a source of white noise. But you can also get red noise processes, in other words, noise that wanders on longer time scales. This here is an example of refraction. So you can also get this larger scale bending of the direction that the radio waves are propagating. And depending on the larger scale structure of the interstellar medium, your times of arrival can wander. So that's an example of a noise process that can be red due to the interstellar medium. And just changes in the overall dispersion measure. In other words, the number of electrons we're looking through can also be a red noise process. Spin noise is a red noise process, so that's that intrinsic long-term wandering of a pulsar's emission. So we can characterize those by their power spectrum. There's different frequency dependencies of those noise processes, and we can use that to distinguish those noise processes from a gravitational wave background. So we can observe particular pulsars and predict their long-term spin noise. This is from Shannon and Cordes 2010, but applied to more recent data. And the interstellar medium, the ionized interstellar medium, would look something like this if you could see it on a large scale. And this is another paper of Michael Lam's from the last few years that shows some simulated dispersion measures from that ionized interstellar medium that's turbulent. And that's why it has this complicated shape and makes these complicated times of arrival. Or these are not times of arrival, but these are dispersion measures, but they change times of arrival on the long term. And the interesting thing about this plot is that it shows, and this is one of the other things that has been dissected in the noise budget interstellar medium groups, it shows that due to dispersion measure variations, you can have both deterministic and random variations. So depending on the, if you had the Earth here and the pulsar here, if you're moving through that line of sight is moving through the interstellar medium, and you happen to be in a region of the interstellar medium that's just linearly increasing its density, well, you're going to see a linear change in dispersion measure. But if you enter these more splotchy regions, you might see something more random. And those changes are also modulated by the Earth's position. So due to the Earth's position, with time, we might be looking through the interstellar medium in a changing way that's systematic, because the line of sight is determined by that annual change in the Earth's position. So that's another deterministic process that can be there. So this is a paper from Megan Jones from this year that models this really nicely and dissects these two components. So one of the things that the noise budget group is working on now, and it's getting more important with the current data releases, is this possibility of frequency-dependent dispersion measures. So you learned about in a previous talk dispersion measures as something that goes as 1 over frequency squared. But if you have wide enough bandwidths, that might be a more complicated law, because if you have dispersion through the interstellar medium, or if you have diffraction rather through the interstellar medium here, that's big enough, you might actually be looking through a different number of ionized electrons. So that can introduce a different kind of dependence, and that's something that's we're preparing for, especially for future very wideband receivers. So, and here's another diagram showing what the interstellar medium can do. Here we have scattering, so it also spreads out the emission in time. And we have propagation through the interstellar medium. That's a frequency to the -4th effect, and that's something that we're also starting to put in our models more and more. But the good news is, and this is a paper from a few years ago from Lean 11, is that most of our pulsars are pretty lightly scattered, and we expect that. I mean, we selected them because they were good. And so far, they haven't been the major timing issue, but we want to keep track of it because it may be an issue in the future. And finally, here's a few plots from another one of Michael Lamb's papers that show this difference between frequency-dependent and dependent noise for different pulsars. And he dissects those. And so that's just kind of a nice plot that brings together the noise budget and interstellar medium groups. And here's another view of that. So I'll stop there, but I hope this was helpful, and please feel free to email me any questions you have.